Okay, the topic is analysis of unbalanced three-phase systems using symmetrical components. So first of all, we have to understand the reasons of unbalanced three-phase systems. So there are different reasons for these unbalanced three-phase systems. That may be different types of faults, series fault or shunt fault. That is open circuit fault or short circuit faults. Then unequal loading on phases and unequal line impedances, unbalanced source voltage, etc. Now, under unbalanced condition, what happens to the voltage or current of the system? So, in this case, we know that for the balanced system, the magnitude of the three phases, phase 1, phase 2 and phase 3 or phase ABC, the magnitude peak to peak should be same, their signal nature should be same, and the phase difference should be 120 degree. But this is the example of the unbalanced phases that is shown in this figure. So here what happens, phase 1, the magnitude is much higher than the other two phases. So those are not equal, and the phase difference that is also not maintained 120 degrees. So here you can see that there is a 140-degree phase difference. Okay, and peak magnitude that also differs. So this is the unbalanced system. So for this unbalanced system, to understand its nature or characteristics, we have to break this system in the symmetrical components. Okay, so the any unbalanced system is break into three symmetrical components, and individually those components are balanced. And there are three types again. So the positive sequence components, negative sequence components, and zero sequence components. So in case of positive sequence component, this phase sequence of these is same as the original phasors. Individually it is balanced and phase difference is 120 degree. So for the negative sequence components, we have, that is the opposite phase sequence of the original phasors. It is individually balanced. Phase difference is 120 degree. For the zero sequence, three are of equal magnitude and in the same phase. So phase difference is 0. So we can conclude that any means that will be proved later. So any uh, phase actually breaks into any phase actually breaks into its positive sequence, negative sequence, and zero sequence components. Okay, so in this is the diagram of different phase sequences. So first on the positive phase sequence. So here, for better understanding, we are keeping A1. 1 signifies the positive sequence. So A1, that is along x-axis. Then the positive for the positive sequence, the B is along this and C is along this. So that is actually same as the original phasor of the system ABC or RYB. So for the negative sequence, the phase sequence is opposite to the positive sequence. So here the ABC for the positive sequence, that is clockwise ABC. But for the negative sequence, that is phase sequence is anti-clockwise A, B, C. So both the cases will consider that A is the reference sequence or reference phase. Acha, for the last one, that is the zero sequence. So the three phases, those are in the same phase. So phase difference is 0 and their magnitudes are also same. Okay. So for the positive and negative, also their magnitudes are same. Phase difference 120 degree. Individually, all these are balanced. Acha. For the positive sequence, VA1 that equal to VA1 with angle 0 because it is reference. VB1, the position of B is B1, that is if we consider clockwise direction with respect to A1, that is minus 120 degree, if we consider this. Okay, minus 120 degree, or we can say that that is positive 240. Okay, so that is shown. So B, that is A1, so minus 120 degree, or you can also write VA1 with angle positive 240 degree. So that equal to A square VA1. So here the A that is introduced, A is a complex number operator. What actually happens, we are just considering this is 1, this axis as A. So per 120 degree shifting, we will consider A, that is multiplied. Again 120 degree shifting, that is A square. Again 120 degree shifting, that is A cube. So this way that will continue, and this is A to the power 4. Again 120 degree shifting, A to the power 5. So this way that will continue. So obviously, now if with respect to A, B position is minus 120 degree, means along this. So that will be multiplied with 8A square, right? So that's why it is A square. Achha. Now for VC1 position is only 120 degree positive shifting. So that's why that should be multiplied with A. So that's why A VA1. For negative sequence, so VA2 again the reference, so that's why VA2 with angle 0. Now VB2, the position is VB2 here, so 120 degree positive shifting. 120 degree positive shifting. So obviously that should be multiplied with A. So A VA2. So magnitude of VB2, VA2, those are same, but VC2, these are same, but the complex operator that will differ because their angles are different. Okay, so similarly VC2 is here. So again 120 degree shifting, positive 120 degree shifting. So that should be A square VA2. And for the zero sequence, all this magnitude VA0, VB0 and VC0, all these things are same. So now the A operator. A operator that is shown here, that can be also written as cos of 120 degree plus J sine of 120 degree. So if we put the values of cos 120 degree here, we can have the value plus J of sine 120 degree here. Okay. So what does it mean? Again, for understanding, I'm just putting the uh, operator phasor. So this is 120 degree shifting A, again 120 shifting A square, again 120 shifting A cube, again 120 shifting A4, again 120 shifting A5. So this way that will continue. So 1 means A to the power 3. Okay, A square and A to the power 5, those are same. Okay, similarly equal to A means and A to the power 4 means same. Okay, so this is also written here. So A means 120 degree angle positive shifting with magnitude 1. So this position. Achha, A square, that is 240 shifting this position. Achha, or minus 120. Achha. Now A to the power 3 equal to 1, that is actually proved here. Achha. A to the power 4 equal to A, that is from here. A to power 5, A to the power 5 equal to A square, that is from here. So that will actually continue. Okay, etc. So now if we put the values of A square in this expression, will get that equal to 0. So all these relations are always true. All these relations are always true. For other part of A, in the calculation if we have, so we have to remember the basic relations between them, and you can solve it easily. Okay, now this A can be represented in the exponential form or rectangular form. So that is A equal to e to the power j 120. That is the first we discussed here. and just putting the magnitude of them, and a square, that means e to the power j 240. A square means the angle is 240, so 240, then cos 240 plus j sin 240, just putting their magnitude here, we have these values. Now similar way, a to the power 3, that is e to the power j 360, so cos 360 plus j sin 360. So after putting this value, we'll have this the magnitude 1. So this to the power 3 equal to 1, that is also uh, can be proved by this expression. Okay, so that is the basic of the a operator.